Alrighty, so today the lab we are doing is the water movement in the ground. So it looks like that. Alright, so if you remember what happens when water soaks in the ground, like it rains, water starts flowing through the ground. Eventually it goes down to a layer that the water can't go through. That layer that the water can't travel through we say is impermeable. So this is a layer of impermeable rock. This section here is where all the pore spaces are filled with water. We call that zone of saturation. Up here the pore spaces are filled with air. We call that the zone of aeration. And then that boundary between the two we call the water table. What we're going to look at today are some things that affect how much water and how fast the water travel through the ground. All right. So what we have here are three tubes that are filled with three different sized particles. All right. And we're going to do a few things to these. First off, we're going to figure out the permeability, or how fast the water travels through these various particle sizes, to see what size lets the water pass through faster. Another thing we're going to figure out is what the porosity is, or how much empty space or empty pore space there is between these various particles here. And then what we're also going to do is figure out how much water retention the various particle sizes have. That's how much water sticks to the particles. All right, so before we do anything else, on your paper, all right, on your lab paper, the side has the report sheet on there. It has the info basically like I have here. Then it says experiment, class average, and theory. So the only thing we're doing right now is the experiment. So only fill out the experiment column, all right? Because we're just doing the one experiment. Normally, if I was doing this in a class with a bunch of people, I'd have each group do this, and then we go through and calculate the average. But we're only doing one experiment for this video. So you're only going to be filling out that first column there that says experiment. All right. So first off, the size of the particles. All right. So we're going to say that trial one is the smallest particles, and the size of the particles here are 4 millimeters. All right. Trial two, the second tube right here, trial two, the particle size is 7 millimeters. And then trial three, the one at the end here, the size of the particles is 12 millimeters. All right, so you want to fill that out on your data table. Next, what we want to fill out is the height of the beads in centimeters. All right, so I'm going from the bottom of the tube to where the top of the beads are. And I do that, and I see that on this one, it's about 31 centimeters. Trial two, for this one here, it is about 34 centimeters. And trial three, right here, it is about 34 centimeters as well. All right, next, it says wetting front travel time in seconds. All right, so right here I have 3 graduate cylinders, and each of them I've already filled up with 100 milliliters of water. So what I'm going to do is pour in 20 milliliters of water into this little flask here. All right. I'm going to pour it in this tube, and I'm going to time how long it takes the water to go from the top of the beads to the bottom of the beads. All right. All right, so do that. Should do this in the right hand. All right, so that took about 4.1 seconds for the small one. All right. Now I'm going to do the exact same thing with the medium-sized one. Take 20 milliliters of water. All right. Reset my thing here. Gonna dump it in here. I'm gonna start timing when the water hits there, stop timing when it gets to the bottom. All right, so that one was 2.4 seconds. All right. Now trial 3, exact same thing, but with the largest size particles. All right. All right, so that one only took 1.2 seconds. All right, 1.2 seconds. Okay, so the next thing you want to do on here is you want to calculate the rate of flow, or how fast the water is traveling through the ground, which is the permeability. So how I go about doing that is I'm going to take the height of the beads and divide it by the travel time. All right. So I pull out my handy dandy calculator, and all right, height of beads 31 centimeters, and travel that distance in 4.1 seconds. So my rate of flow for trial 1 was 7.6 centimeters per second. All right. For trial 2, the height of the beads was 34. It traveled that distance in 2.4 seconds. So 34 divided by 2.4 equals, its speed was 14.2 centimeters per second. All right. Now trial 3, I'm not going to do for you. You're going to have to do that on your own. All right. So what you want to do is the height of the beads divided by the wetting front time. So this number here divided by that number there gives you that number right there. All right. So the height of the beads divided by the wetting front time gives you the rate of flow. So you got to calculate that one on your own. All right, next, what we want to figure out is the amount of water required to fill the pore spaces. All right, the amount of water required to fill the pore spaces. Now, I didn't mention it before, but how much beads I put in all 3 containers. I put the same amount of beads. There's about 300 milliliters worth of beads in each of these containers. All right. Now there's a certain amount of empty space between the beads. What we want to do is we want to measure how much empty space there is. Okay. Now how we can do that is to see how much water it takes to fill up the empty space to get up to the top of the beads right there. Now I already poured 20 milliliters in, and I already poured 20 milliliters in. Had a little bit leak out the bottom, so I'm putting it back in. All right. So what I'm gonna do is I'm gonna pour the rest of this in there, all right, because remember I started off with 100 and I took 20 out to pour it in initially. So you wanna see how much of this rest do I need? All right, so it looks like I'm gonna need a little bit more than 100. So I am going to pour another 50 in here. And we'll add 10. All right, still not up there yet. So we'll add another 10. And that brings the water level pretty much right up to the beads right there. All right. So I had the 100 milliliters of water initially, and then an extra 20 milliliters in there. So all said and done, I had to add 120 milliliters of water to get up to the top there. All right. So water required to fill the pore spaces, this was 120 milliliters. Now, same procedure for the second one here. All right. Again, I already put 20 in there. So here's the other 80. And again, it's not quite up there yet, so I'm gonna so add this, I'm gonna add another 10. It brings it up to about there. Add another 10. And I've lost a little bit. Oh, this is leaking a little bit, so I'm losing a little bit out of the bottom. Let's see how much I lost here. Add another little bit there. But there's about another 5. And right now, it's pretty much right up to the top there. So that one took 125 milliliters. All right. The last one here, same thing. I already put 100 milliliters, or excuse me, I already put 20 milliliters in there. So I'm adding the other 80. All right, so that leaves me short a ways. So that. And that takes me pretty much right up to there as well. So that was about 120, that was about 125 as well. All right, next. Percent pore space, all right? Now, how I go about finding that, I just told you a little while ago that each one of those I added 300 milliliters of beads to, all right? Added 300 milliliters of beads to. All right, so how I go about finding the, water required, or the percent pore space, is there's 120 milliliters that I put in there out of a volume of 300 milliliters of beads, all right? So I pull out my calculator and I do 120 divided by 300. That works out to be 0.4. So I take that whole thing and I multiply that by 100. So that works out to be 0.4 times 100 would work out to be 40%. All right. So my percent pore space for the trial 1 was about 40%. All right. Now for trial 2, all right, same procedure. All right, so I had to pour in 125 milliliters to fill the pore spaces. There was about 300 milliliters of beads in there. So how I go about finding it, I do 125, how much water it took to fill. There are 300 milliliters worth of beads. I take that whole thing and I multiply it by 100. So I go 125 divided by 300. Works out to be 0.42 times 100. Works out to be 42%. All right. So for where it says percent pore space, I'm going to write 42%. All right. And then for trial 3, it's going to be the same thing here. So same procedure. I got 125 is how much water it took to fill up the particles. There were 300 milliliters of particles. So what you want to do is take that number right there, divide it by 300. So 125 divided by 300, then times 100 to make it a percent. All right, so that's the number you're going to write right there. So that number right there is how much water it took to fill it up, divided by 300, because that's how many milliliters of beads there were, and then 125 divided by 300, then times 100 to make it a percent. That's what you're going to write right there. All right. Next, it says water recovered. All right, so how we're going to go about doing that is I'm going to open up the bottom of the tube here. I'm going to let the water drain out. All right, so that's how much water came out the bottom. All right, so I want to measure that. So I'm going to take that, pour that in my graduate cylinder right here. All right, so the amount that came out the bottom is just a smidge over 100. So it's about 101 or so. So I poured in 120 milliliters worth of water, and 101 came out the bottom. So the amount of water retained is going to be the difference between those two. So 120 minus 101 means that there were 19 milliliters of water retained right there. All right, now for this guy here, I'm gonna let the water come out the bottom. All right. So there's 100, and about 15. All right, so about 115 is what came out the bottom. All right, so I poured in 125, 115 came out the bottom. That means the amount that's retained by the particles was about 10 milliliters. All right. All right, now the last one here. All right, so for that one, so there's 100. All right, and works out to be about 20, so about 120. So the water recovered was 120. Right. So I poured in 125, and 120 came out the bottom. So if I want to calculate the water retained, I do 125 minus 120. That'll give me the number I get right there. All right. So now that I have this data, what I'm going to do is I'm going to go over to the graph, and I'm going to graph it. So I'll move this out of the way a bit. All right. So the first graph you have on there is your graph in particle size and permeability. All right. So my first one, my particle size of 4, my rate of flow is the permeability. So particle size 4, I go to line 2, the rate of flow, and that is 7.6. So I go on my graph, 4 and 7.6, you plot it right about there. All right. Trial 2, my particle size was 7, and my permeability is the rate of flow right there. So my permeability would be the 14.2. So particle size 7, rate of flow 14.2. So particle size 7, 14.2 is right about there. And then you're going to do the same thing for the last one. You do the particle size 12, and then whatever number you calculated for line 2, that number right there, you're going to plot 12 millimeters, and then you plot your point, and then you're going to connect them with the line. So you connect those two, and then your third point will be up here someplace, and you connect that with the line. Second graph, all right? I got particle size and pore space, all right? Or percent pore space. So I look up here, and I have particle size of 4, and my percent pore space was 40, all right? So particle size 4, 40% would be right about there. Next one, trial 2, particle size 7, percent pore space I got was 42. So 7, 42 be right about there. Connect those two. And then you go to your trial 3 data, particle size 12, and then whatever value you calculated over here for your pore space, you're going to plot that over here and then connect the line. All right. Next, for the water retained. All right. So particle size 4, my water retained was 19 milliliters. So 4, 19 will put me right about there. For trial 2, particle size 7, and my water retained was 10. So 7 and 10. Connect those two. And last one, particle size 3, whatever number you got right there, all right? I'd go particle size 12, then plot the point, and then connect that with the line, all right? So the main things you should notice from this when you finish your graph is that the larger the particle size, the greater the permeability. In other words, the bigger the particles are, the faster the water soaks through the ground. As far as porosity goes, so my values there, the graph really didn't move. There's a couple percent difference, but that's probably just errors in measurements and the tubes were leaking a little bit and stuff like that. For the most part, that graph is pretty much a straight line across. So with the particle size and the percent of pore space or the porosity, what you should notice is that there really isn't a relationship there. Particle size does not affect the porosity. And the third thing you should notice here is the particle size and water retention is that the bigger the particles are, the less water was retained or the less water there was sticking to those particles. And the reason for that is that smaller particles have more surface area than larger particles, and as a result, less of the water, or excuse me, as a result, more of the water sticks to the small particles and less water sticks to the bigger particles. Now, one other thing I want to address, don't really have a demonstration for it, so I'll just kind of do it as a drawing up here. Another thing that can happen to water in the ground is sometimes the water can move up in the ground, all right? Now, so let's say like these containers right here, if I took these and they were nice and dry and I stuck them in a pool of water, all right? What would happen is some water would actually go up in the tube, all right? And the upward movement of water in a tube or in material is called capillary action. Now, how high the water goes up in the tube is going to be dependent on how big the particles are. All right. So let's say I took those 3 tubes there and I stuck them in water. So that would be like the tube for trial 3 with the big particles. Here's a tube from trial 2 with the second particles, and here's a tube from trial 1 with the smallest particles. What I would end up noticing with this is that with the big particles, maybe the water would go up that much. Right? With the medium-sized particles, maybe the water would go up that much. With the smallest particles, maybe the particles would go up that much. Okay. So what you would notice is that with the smaller particles, the water went up higher, and the bigger the particles are, the water didn't go up as much. The reason for that is has to do with the surface area again, and how big the spaces are. With small particles, there's narrower spaces, and it's easier for the water to go up narrower spaces because there's more surface area for the water to stick to. When you have bigger particles, the spaces are bigger, and there's not as much surfaces for the water to stick to, so as a result, the water doesn't go up as much. So for capillary action, small particles, the water goes up a lot. Big particles, the water only goes up a little bit. All right, so that's it. So you should have all your data tables filled out right there, your report sheet all done. You should have your graphs done, and now you have all the information you need to answer the questions. All right, and that is that. So water movement in the ground.